Yeah.
Okay, we are live on YouTube now. So I'm going to start the introduction. Welcome to the Earth to Earth seminar. Thank you for joining us today on the 15th of October, 2020. Please visit our website, earth2earthseminar.com, for information about the series. Earth to Earth is organized by a governing board with representation from UK universities, Nature Geoscience, and the British Geological Survey. Any UK institution that wishes to have a representative on the board should contact us by email. Today, we welcome student societies from participating institutions to get in touch with us to co-organize and promote seminars. Today, we have partnered with the Cambridge Centre for Climate Science. We welcome their members. It's the mission of Earth to Earth to engage the UK geoscience community with inspiring science from internationally leading researchers. We'll do this while promoting inclusivity, diversity, and supporting the advancement of early career researchers and highlighting geoscientists' contributions to addressing global environmental challenges. Earth to Earth seminars take place every 2 weeks at this time and day. They are open to everyone. You can join via Zoom webinar or via the live stream to YouTube. The lecture will be recorded and with speaker permission will be available on the YouTube channel with closed captioning. Calendar, links, and further information are on earth2earthseminar.com. During seminars, we ask that you follow our code of conduct, which you can find on Earth to Earth webpage. For questions, please use the Q&A channel, which you'll find at the bottom of your Zoom window. Questions may be posted at any time during the seminar, and anyone can upvote questions that they like. We'll have 10 minutes at the end of the seminar for me to relay your questions to the speakers. And now it's time. Now it's my pleasure to introduce today's co-speakers. We're very fortunate to have Professor Natlya Gomez of McGill University in Montreal and Professor Jerry Mitrovica of Harvard University in Boston. Natlya Gomez is a professor at McGill University and a Canada Research Chair in the geodynamics of ice sheet sea level interactions. She did her PhD at Harvard and in Earth Sciences and her postdoctoral work at the Courant Institute of Mathematical Sciences at NYU. Jerry Mitrovica is the Frank B. Baird Jr. Professor of Science at Harvard University and former J. Tuzo Wilson Professor in the Department of Physics at the University of Toronto, where he also received his PhD. His many awards include the Love Medal from EGU. So thank you very much, Natlya and Jerry, for agreeing to be with us today, and please begin your talk.
Okay, thank you, Rich. So I've changed the title of this talk a little bit, and Natlya and I realized in preparing the talk that our focus is really on how a deepening of the understanding of the geometry of sea level changes has really advanced our understanding of climate change, both in the modern world and in the geological past. So I'm going to use that title as I go forward. Well, if I'm going to summarize Ice Age dynamics and Ice Age sea level, this is a good place to start. This is an oxygen isotope stack from an important paper by Lorraine Lisicki and Mo Ramo from about 15 years ago, showing variations in oxygen isotopes going back in time. Just a really broad inspection of this, one can see the 100,000-year cycles, the transition from the obliquity-dominated 40,000-year cycles at about 1 million years ago. I'm going to be discussing an application on marine ice sheet, marine isotope stage 11, as well as the modern world. For those who aren't familiar with this sort of stack, everything up here means less ice. This is an interglacial sea level, interglacial period. Up here, we're in glacial maximum, the last glacial maximum and the penultimate here. Now I'm going to talk about sea level, and I'm going to give you sort of a primer on the physics of sea level, in part to introduce the sort of work that Natlya is going to be discussing. If you're interested in the physics of Ice Age sea level, this is the place to start. A paper from the mid-1970s, Bill Farrell and Jim Clark, which was the first to provide a mathematically coherent and physically self-consistent theory for Ice Age sea level changes. This picture is often reproduced, but people don't understand the subtlety in the image, right? The image is showing a glacier that is melting going from here downwards. And if you're sitting here on some tropical beach, you're seeing sea level rise from 0, 1, and 2. But what people don't understand in looking at this is that the beach closer to the glacier, sea level is actually falling due to the deglaciation. So this picture is worth more than a thousand words. It was something that my group revisited about 20 years ago in describing the fingerprints of sea level change that I'll talk to you about in a little bit more detail. Okay, I'm going to show you, and this is it, a numerically predicted rate of sea level change during an interglacial period. And by that, I mean this is the sea level change that one expects as one comes out of an ice age cycle when there's no more ice volume changes. There's no contribution to this image from the direct contribution from the melting of ice sheets, the entrance of meltwater into the oceans, right? So I'm going to give you a primer on this and talk about an application, an important application by Moremo and I that focused on marine isotope stage 11. But here's the primer. First thing I want to tell you is this color bar here is in millimeters per year. The blues and reds you see in high latitudes in the north and south are entirely saturated here, right? These reds exceed a centimeter per year in amplitude, which is well off to the left of this plot. The blues exceed 3, 4, 5 millimeters per year, which are well off to the right side. I'm taking this figure from a paper by Glenn Milne and I, which focused on this far field sea level change. But I have to warn you that there is a saturation at high latitudes. Okay, so let's look at some basic ice age sea level physics, right? Here I'll start with the near field, these regions of hot red and blue, both in the north and the south. When an ice sheet grows on the crust, it produces a subsidence of the crust beneath it. It also produces an uplift at the periphery. These are called peripheral bulges, just through a conservation of mass. If you're causing a subsidence in one place, uplift has to happen in another place. And it happens in a region that encircles the previous locations of the ice sheet. When an ice sheet melts, the crust below it begins to uplift. This is the classic problem of post-glacial rebound. And at the same time as that uplift occurs, the peripheral bulge that had been uplifted begins a subsidence. When you move out of a deglaciation into the interglacial period, this process continues. That's what's shown on this bottom frame here. The uplift continues and the subsidence of the peripheral bulge continues. So in the near field here, these red regions represent zones in which sea level is falling by, even today, by amplitudes of a centimeter per year or more due to this post-glacial rebound. And I should say that sea level is defined as the height of the sea surface relative to the sea bottom. So sea level can change both because the sea surface height changes or the sea bottom. So in these red regions, what we're seeing is a post-glacial rebound of those crustal regions that's leading to a sea level fall. The blue regions, these are these peripheral bulges. They're zones during an interglacial of crustal subsidence. That crustal subsidence leads to a sea level rise that can reach amplitudes today of 3 or 4 millimeters per year. And they give you a clear understanding of why figures like this are so important. If one is looking at modern sea level change, looking for sort of global warming, anthropogenic effects, and one has to correct for that sea level field using predictions of this kind. And so this field tells you that the US East and West Coast, even in the absence of any anthropogenic effects, would be experiencing today sea level rise on up to 2, 3 millimeters per year because of ongoing residual ice age effects. We're now 7,000 to 8,000 years from the end of the last ice age cycle. We're still experiencing these effects. Let me now move to this far field, this sort of light, I show a picture here first. This is a picture of Bathurst Inlet in Nunavut. That's in sort of northern Hudson Bay here. What it's showing here is that a beach formed at some point in the past. Post-glacial rebound led to the emergence of this beach above sea level. The next beach formed and so on. And that process continues until you produce what geologists sort of fancifully calls flights of raised beach terraces, these parallel terraces of ancient beaches. Let's look now into the far field here, okay? What is happening in the far field that causes this sea level fall reaching magnitudes of about 0.5 millimeter per year? Well, let me augment the picture I've shown you earlier with a kind of cut into the far field. As ice sheets grow and the peripheral bulge uplifts, that uplift of the bulge displaces water towards the far field, and it leads to a rise in sea level in far field locations, right? When that process ends, deglaciation starts. Uplift here and peripheral bulge subsidence in particular reverses the process. The peripheral bulge now subsides, and as it does, water moves from the far field into the near field and causes a lowering of sea level. That process, again, continues even in interglacial. And so what is happening in this figure is that as these blue regions encircling these locations of ancient ice cover subside, these peripheral bulges subside, water moves away from the far field into those regions to fill the accommodation space that's formed by the subsiding peripheral bulges. That process is called ocean siphoning. It may seem to be small to you, 0.5 millimeter per year, but it produces significant effects that are evident in the geological record. This is a figure, I think it's from Malden Island, which is in the equatorial Pacific. This sort of feature is pervasive in the equatorial Pacific. They're called 3-meter corals or 3-meter beaches. The top of this coral is dated to about 6,000 years. That's the end of the melt phase. And it's now 3 meters above sea level. And one can see these sorts of, in addition to these sorts of corals, one can see ancient records of beaches that are now 3 meters above sea level that are dated to around 6,000 years. Well, 0.5 millimeter per year doesn't sound like much, but if you go back in time 6,000 years, you get a sea level fall or drawdown of 3 or 4 meters in these far field locations. If you were sunning yourself somewhere in the equatorial Pacific, you might think the last thing that's causing this sea level fall is the ice age, but indeed it is. It's the ongoing effects of the ice age that are now being masked, of course, by sea level rise associated with modern melting, but not in the last 6,000 years. Okay, so let me show you a couple of quick applications of these ideas and why they've been important in sort of understanding climate change in the past. I'm going to talk now for a few minutes about marine isotope stage 11. Okay, that happened 400,000 years ago. It is the longest interglacial of the last million years, not only the last 500,000 years. There is geological evidence from Bermuda and the Bahamas that sea level peaked at 20 meters above modern sea level during this period. And if that's true, that would be very important because it would indicate, this is an example of a picture taken from a paper on these ideas, that would indicate that you would have had to collapse the West Antarctic ice sheet, the Greenland ice sheet, and even cause significant melt from the East Antarctic ice sheet, which today is considered to be relatively stable. This has led to all sorts of controversy, back and forth arguments, some suggesting that this peak global mean sea level was in fact an indication of collapse, others saying no. These are just indicating deposits from mega tsunamis that have happened around 400,000 years ago. And putting aside the geomorphological problem of deciding between these two things, let's see what an ice age sea level physics tells you about this. Well, as I've said to you, in the peripheral bulge of ice sheets, sea level continues to rise during an interglacial because of the subsidence of that peripheral bulge. Okay? So as that interglacial proceeds, that subsidence proceeds, sea level rise proceeds. Bermuda and the Bahamas are both in the peripheral bulge of the Laurentide ice sheet that covered Canada in the glacial cycle preceding MIS 11. And I want to reinforce that there's no ice volume change in this particular numerical prediction, right? Okay, so because of what I've told you, if you're looking at a sea level record in the Bahamas or Bermuda, you would expect that high stand to have been produced at the end of the interglacial because sea level will rise throughout the whole interglacial, right? So the question is though, what would that high stand look like? What does it look like today? Where is the predicted high stand of marine isotope stage 11 relative to the present day? Okay, to answer that question, we have to remember something quite subtle. Marine isotope stage 11 lasted 15, 16,000 years. Our present interglacial has lasted only half that long, right? So that means during marine isotope stage 11, sea level had more of a chance to rise than it did at present interglacial. And that means that a high stand at MIS 11, right, will only reflect this distance, not the total distance of the sea level rise that occurred during that interglacial. Because we're here at the present day, and we're looking back towards where a beach that was formed at marine isotope stage 11 would have been formed. So we're really sensitive to the difference in disequilibrium, isostatic disequilibrium in MIS 11 relative to the present interglacial. And that disequilibrium, that difference is shown here. This is, in fact, what a beach that was formed at the end MIS 11, what height it would have relative to present day due to ice age effects. And in Bermuda and the Bahamas, that's about 10 meters. So this is an ice age effect that must be corrected before one makes any inference of excess melting, because none of the predictions I've shown you have any excess melting of the polar ice sheets, right? And so when you do that, you realize that that 20 meters, half of the observation of that 20-meter high stand comes not from excess melting of polar ice sheets, but rather because of this difference in isostatic disequilibrium, right? And so this implies still, this is not the greatest of news, it implies still that the West Antarctic ice sheet and the Greenland ice sheet certainly collapsed, but that it suggests a relative stability of the East Antarctic ice sheet during marine isotope stage 11. I don't know why that's there. I know. These figures were figures for the interglacial. I emphasized to you that they were figures that did not include the signal from contemporaneous melting of ice sheets during an interglacial. So now I want to focus on that signal. What happens to sea level during a period in when ice is melting, right? Well, I can ask the question, what would happen to sea level if the Greenland ice sheet melted? Okay, I can do a numerical prediction of that. And your intuition may be exceedingly wrong when you see this solution, right? Three things happen when an ice sheet melts. The first thing is you're certainly dumping meltwater into the ocean. You're increasing the mass of the ocean. You're also causing the crust to rebound. I've already talked about that, right? But the third thing that happens is that you relax the gravitational attraction that the ice sheet has on the ocean. Ice sheets, just like the sun and the moon, exert a gravitational attraction on the ocean. They're not as massive as the sun or the moon, but they're a lot closer to the ocean, right? When they melt, that gravitational attraction is reduced and water migrates away from the location of the ice sheet. So the coupled effects of crustal uplift and the migration of water away leads to a sea level fall close to a melting ice sheet. That sounds counterintuitive, and how do we define close? Well, close is not very close. Close is 2,000 kilometers away, right? So if the Greenland ice sheet melts catastrophically today, sea level will fall within a radius of 2,000 kilometers of that ice sheet, right? If you have a friend in Scotland or Norway, or as a Canadian, I can say Newfoundland, then you shouldn't be concerned about the melting of the Greenland ice sheet. Well, except in a more general humanistic sense, you should be concerned. But in those locations, sea level will actually fall. This is a numerical prediction of the sea level change that would happen if you melted enough ice that global average sea level rose about a meter. This effect is not small. If enough ice melts from the Greenland ice sheet to raise global average sea level a meter, sea level will fall, sea level and the shore of Greenland will actually fall 10 to 20 meters, right? This gravitational effect is significant. And as all ice sheets and glaciers have their own distinct pattern of sea level change, because this pattern depends on the location of the ice melt, right? And because of that, this is a pattern for Antarctic ice sheet melting. Sea level, these geometries have come to be known as sea level fingerprints. And modern sea level analyses have moved away from simply estimating global mean sea level to looking, whether it's in satellite records or tide gauge records, instrumental records of modern sea level change, trying to answer, I think, a more important climatological question, which is, where is the meltwater coming from? And using these fingerprints, one can deduce that if you have enough accurate measurements of the geographic variability in sea level, right? I wanted just to highlight some results from a paper by two of my former students, Carling Hay and Eric Morrow, that use these fingerprint ideas within a more sophisticated statistical formulation to analyze tide gauge records. Tide gauge records exist at all of these black dotted sites, right? To try to reassess 20th century sea level rise, right? I won't go through the details, I don't have the time, but I'm of course happy to answer any questions about it. The main thing is that the statistical techniques embedded within it the physics of fingerprints. It used a Bayesian philosophy that essentially combined measurements with model-deduced covariances of sea level around the globe. And Carling and Eric came up with a new estimate of 20th century sea level rise that was 30% lower than previous estimates. 20th century sea level rose by about 1 millimeter per year, not 1.5 to 2 millimeters per year. And I guess predictably, when this paper was published, despite the fact that the abstract was quite careful in its wording, a number of people suggested, well, climate change is not happening. You know, they've reduced the level of sea level rise in the 20th century, and eventually they're going to reduce it further still until it gets to zero, right? But they missed the big picture conclusion of this paper, and that is nobody disagrees with what sea level has done in the last 20 years. So if you've reduced your estimate of 20th century sea level rise, what you've effectively done is significantly increase the inferred acceleration of sea level change from the 20th to 21st century. And so that was really the take-home point. So I hope with these two applications, I've given you a sense now of how the geometry of sea level change can provide a lot of insight in these climate events, whether they took place in MIS 11, 400,000 years ago, or in the modern world. So now I'll turn the mic over to Natlya Gomez, who's going to talk about some of this really impressive recent work that she's been doing. Natlya?
Thanks, Jerry. I'm just going to start sharing my screen. I think you have to stop sharing your screen first. Oh, there.
It says I have stopped. I don't think I did it. Somebody else did that for me.
Okay. And okay, thanks, Jerry, for giving that nice introduction, and also to the Earth2earth seminar team for it's great to be able to talk across an ocean with you. So to sort of continue on from Jerry's introduction to sea level change following sort of ice loss from an ice sheet, these are these same predictions of sort of the pattern of melting that we see from melting from the Greenland ice sheet on the top and the West Antarctic ice sheet. And as Jerry said, when you move close to the ice sheet, these region in red, then if we zoom in on this sea level fall close to the melting ice sheet because of gravity and deformation, we get up to an order of magnitude or more larger sea level fall close to the ice sheet than we do see a sea level rise farther away. And so what the second sort of part of this talk is going to focus on is zooming in on this region where ice sheets are evolving. How does the sea level change, this sea level change feed back onto the dynamics of the ice sheet itself? And this is particularly relevant for the Antarctic ice sheet because there are so many regions of marine-based ice in the Antarctic, especially in the western portion of the ice sheet here. And these regions sit on bedrock that lies below the height of the sea surface, and they interact very strongly with the surrounding ocean. And they're particularly considered unstable in a warming climate in that when the slope of the bed is reversed, there's a marine ice sheet instability mechanism that takes place that leads to sort of ongoing retreat without need for further climate forcing. And so just to walk you through how this works. So here's a cross section of a marine ice sheet. It's gaining most of its mass through accumulation or snowfall from above and flowing outwards under its own weight and losing most of its mass through ice loss across this grounding line into floating ice shelves that sort of calve off into icebergs and go off into the ocean. And it turns out that the ice loss across the grounding line is strongly sensitive to the thickness of ice there. And just by sort of a isostasy argument, this is in turn proportional to the depth of water. So if you change the depth of water, or if you retreat into a deeper area of ice, then area of bed, then the ice loss across the grounding line is going to increase. And so this is the reason why, if we look on the right, if we retreat this grounding line into deeper water, then we're going to see an increase in ice loss across the grounding line, which leads to further retreat into further deeper water, and so on. And so this is the instability mechanism. But another way, other than retreating the grounding line into a new position to change the water level, of course, is by changing the water level, melting ice and changing the water level itself. And so if we consider the effect of a sea level rise, say an ice sheet far away from the West Antarctic melts, raises sea level in the Antarctic, then this leads to increased ice loss across the grounding line that is coming in and initiates a grounding line retreat. Or if the grounding line is advancing, then this effect would sort of slow the grounding line advance. And we've looked at this as an example of the Northern Hemisphere ice sheets evolving over the last ice age significantly changed sea levels in the Antarctic. And we see that actually this sea level forcing from the faraway Northern Hemisphere ice sheets has a significant impacts of amplifying ice growth and retreat in the Antarctic, and leading to a more dynamic retreat through the last deglaciation. But the next thing that I'm going to sort of focus on for the next part of the talk is what happens to the ice sheet when it melts and changes sea level around itself. So in this case, we know that when the Antarctic ice sheet melts, this leads to a local sea level fall that's quite large. And this in turn reduces the ice loss across the grounding line. And this can initiate grounding line advance from steady state, or if there's an ongoing retreat, then you could slow or stop the retreat with this effect. And so just as an example of how this works, this is sort of a flow line ice sheet, a simple flow line ice sheet model simulation where there's a fixed bed and sea surface, and the marine ice sheet instability is in play and the ice sheet retreats all the way. But when we include this sea level fall due to gravity and deformation, then this reduces the depth of water at the grounding line. And in this particular scenario, this is enough to slow and then stop the retreat from happening. And so this is so far a sort of simplified flow line experiment, but the next step of this work is that we've coupled a full global sea level model to a dynamic model, a more realistic dynamic model of the Antarctic ice sheet. And so the way that this coupling works is that the ice sheet model evolves through time for a period, influenced by the changing climate, and feeds ice thickness changes to a global sea level model. And this sea level model computes sea level change everywhere, including the change in bedrock elevation beneath the ice. And so that gets fed back into the ice sheet model and updates the ice sheet model's bedrock elevation. And the model marches forward in this way. And so one of the strengths of this type of model is that we can predict not only sort of ice dynamics and snapshots of how the ice sheet is evolving in response to the changing climate, but also predictions of the global sea level changes that would occur from this ice loss, which can then be compared to, for example, far field sea level records. So when we apply this model to look at the last deglaciation, what we find here is this is a simulation including the coupling and not including it over the last 40,000 years. And what we find is, as expected, that ice sheet growth and retreat over this time period is dampened when we include this sea level feedback into the calculation. And this type of model has been developed by a number of other groups now, and they find similar effects over this time period. And I just wanted to mention that while we're focusing on the Antarctic, There were other ice sheets, some of which were marine-based, and a graduate student of mine, Holly Hahn, is looking into the effects of deformation and sea level change on Northern Hemisphere ice sheets over this time period. And she's finding in particular that, of course, the elevation of the ice in the atmosphere is also impacted by these sea level changes and deformation. Okay, so we understand that this sea level feedback is active and that it acts to dampen ice sheet growth and retreat. But what I haven't told you yet is that these simulations all include just a single radially varying model of Earth structure. And Earth structure or rheology determines the rate and sort of spatial pattern of deformation that occurs. And so these simulations and the strengths of the sea level feedback really depends on the Earth structure. So in the Antarctic, we're in a really unique setting with the Earth structure. These are cross sections of seismic tomography beneath the ice sheet in the Earth. And what we see here is that in regions in blue in the East Antarctic, these show higher seismic wave speeds, which is indicative of sort of a thick cratonic structure there with a thick lithosphere and higher viscosity. But if we move to the West Antarctic, then we see a lower than average viscosity structure, or slower wave speeds that are indicative of a lower viscosity. And if we look at GNSS studies, these infer viscosities of down to about 10 to the 18 Pascal seconds, which is several orders of magnitude lower than on average. And so what this means is that these areas, viscous effects are occurring, sort of relaxing on decadal timescales, perhaps, or centennial timescales, instead of the typical millennia that we think of for these sort of ice age uplift effects. And of course, the structure across the West Antarctic even is still laterally variable. And so this laterally varying Earth structure is going to impact the magnitude and timing of the sea level change, which in turn feeds back onto its effectiveness to sort of dampen the ice loss. So if we take into account this 3D Earth structure, this involves sort of a great increase in computational cost. But if we incorporate a 3D Earth model into our global sea level model and repeat this coupled simulation, then what we find is that predictions of uplift rates in the modern, as well as sea level throughout the simulation, as well as local ice loss, are impacted by this 3D structure. So just to walk you through a couple of examples, this is on the top left is a prediction of the uplift rate at the modern from an ice age simulation through the last deglaciation. And you can see, that there's uplift in regions that experienced ice loss. And on the right, what we see is a difference between this prediction and one that assumes an average radially varying Earth structure model. And so what we find is that there's a significant difference in local areas between these two predicted uplift rates. And this would have a significant impact on trying to interpret the contribution of ice age effects to GPS or GNSS records in this area. There's also a difference in interpreting paleo sea level records. So just as an example, these are records from Larsen Hills in the East Antarctic. And in this region, the predicted relative sea level using a radially varying Earth structure that's higher viscosity is too high compared to the records. But this area is on the edge of the craton. It's actually lower viscosity than on average. And so if we incorporate that 3D Earth structure, then this means the uplift happens sooner in the model and it lowers the prediction of relative sea level. And so here we see we're able to better understand the records in this area. So far we've talked about the past, but if the Earth structure is deforming on decadal or centennial timescales, then this has implications for modern and future melting as well. So this is from a recent paper by Evelyn Powell et al., looking at the contribution from these viscous deformation to sea level changes or modern uplift rates of the solid Earth in response to modern and future ice melt. So what we found is that for modern melting over the last couple of decades, we're already seeing a contribution from viscous effects. And if we go forward in time, even 50 years, then these viscous effects are amplifying the uplift rates that we're predicting by up to 50%. So this is sort of relevant for looking at, in turn, how do these influence the future evolution of the ice sheet. So here I'll walk you through an example of an earlier paper where we looked at using the coupled model to look at the future evolution of the Antarctic ice sheet. So in this experiment, we applied sort of a simplified climate warming, instantaneous climate warming at the beginning of the simulation, quite mild. And this is sort of the evolution of the volume of the ice sheet, or its contribution to global mean sea level over time. And so you can see the marine ice instability hypothesis is at play, and the ice sheet retreats in response to this warming. Now, with the red line, if we incorporate the sea level feedback with sort of an average global Earth structure, then we see as expected that the ice loss is dampened and slowed in this scenario. But if we include instead a sea level model that captures the Earth structure, sort of representative of the Earth structure underneath the West Antarctic, then what we see is that the uplift happens sooner and is more localized to the grounding line where you're loading. And this means that it's more effective at stabilizing the ice sheet. So in this particular scenario, we see that the ice sheet stabilizes rather than retreating. And this sort of stabilization occurs around the Amundsen Sea sector of the ice sheet. And so this suggests that this effect could be important for understanding future ice loss as well. But of course, since this time, there's been a lot of ongoing work. This was a sort of simplified climate forcing. We can do climate more sophisticatedly now. There's suggestion that we need to look at the resolution of the models to capture grounding line dynamics and deformation in these areas. There's also been introduction of new mechanisms such as the marine ice cliff instability mechanism, which further promotes ice loss in these areas. And so this is sort of ongoing work to account for all of these in order to be able to make more accurate projections of these effects. But this is just a sample simulation in which we've assumed a very rapidly deforming bed everywhere and compared it to a case where the bed is rigid. So looking at the effect of deformation on the ice sheet here. And what we see is that it could have a significant effect, even with stronger climate forcing and even with including the marine ice cliff instability. And so this is sort of ongoing work with a new postdoc in our group through the PolNet NSF project. Mariam Yousefi and a graduate student of mine, Jeanette Wan, are looking into these issues. Okay, so I'm just going to wrap up by taking a step back to the globe again and thinking, projections of the Antarctic ice sheet are quite wide-ranging in response to future climate. And this sort of uncertainty in the projections can have significant implications for far-field coastal communities and environments. So this is work that's just about to come out, done by my graduate student Anna Hayden and Sophie Wilms from Bangor University. And what they looked at is coming back to the Hudson Bay region that Jared talked about at the beginning, looking at how is sea level going to evolve in these regions and how in turn might that feed back onto ocean tides in this area. And so what we find on this column here, we're considering this area is currently uplifting from the last ice age and water levels are dropping, as Jared has said. And so for a simulation where we consider that the Antarctic ice sheet is on the low end of what it's going to contribute in the coming centuries, then this is the predicted sea level change, considering this and also considering Greenland, but Greenland is actually not really contributing here because it's close enough that it's sort of on the zero line of the Greenland fingerprint. So really this is controlled by glacial isostatic adjustment and Antarctic ice loss. And here we see that if Antarctica doesn't contribute too much, then the sea level fall in this region is going to continue in the coming centuries, with sort of some more minor implications for ocean tides here. But if we consider the high-end projections of the Antarctic ice loss, then there's actually a reversal in sign of the sea level change a couple of centuries into the future. And so then sea level goes from falling due to ice age uplift to rising due to Antarctic ice loss. And if we put this into updating the bathymetry in the tide model, this has a significant change in the nature of the ocean tides and the amplitude of tides in this region. And this is a region where there are a number of coastal communities. This is a map of coastal indigenous communities in the Canadian Arctic. And these communities and the environments are sort of strongly dependent on the water levels and the impact of these water level changes on the surrounding environment. So one of the things that we're sort of missing in these areas right now is monitoring, sort of dense monitoring in the way that we can do for more populated areas. And so one of my graduate students, Dave Purnell, is working on developing more accessible water level monitoring systems that are designed for these remote environments and sort of accessible to use by communities to better monitor the situation in these areas. So, and with that, I will wrap up, and hopefully we've got across to you that, you know, ice dynamics and sea level change and even solid earth deformation are really linked across space and time, both past, present, and future. And finally, that this has implications for making better projections and in turn for coastal communities and environments in the face of ongoing climate change. So thank you for your attention. Happy to answer any questions.
Thank you very much, Jerry and Natalya, for the excellent talk. We have about 15 minutes for questions, even a little bit more. And we have 3 in the Q&A window. And anybody who has a question they'd like to add, please add it to the Q&A channel down at the bottom of your Zoom window. I'll read the first one, which comes from Kian. Natalya, why do each of those appear almost opposite? And I'm not actually sure what this refers to, but it goes on to say the 3D, 1D model shows subsidence in the west and mild uplift in the east, while the other shows uplift in the west and subsidence in the east. Natalya, do you understand what this is referring to?
I think I have an idea. Let me just go back to the slide that I think it's referring to. So I think the question is here, why do we see this sort of difference in signal so in these red regions, this is the modern uplift rate, the ongoing deformation of the Earth in response to this past loading. And so where we've had this major retreat of marine ice in these red regions, the land is still uplifting from that ice loss in the modern. Whereas in the center of the ice sheet, when you warm the climate, you also increase snowfall. And so you can have a little bit of an accumulation of ice in the center. And so this is the sort of contribution from that small increase in snowfall in this area. And you also have sea levels evolving here, not only due to the Antarctic ice sheet, but also due to the Northern Hemisphere ice sheets having retreated and contributed a sea level rise in this area. And I think some of the differences that you see, the sort of large scale pattern is quite similar in the 1D case, but you see different localized evolution of the ice, especially during the Holocene, where it's sort of strongly being affected by the changes in bedrock elevation at the grounding line. And so some of the difference that you see is just a difference in the Earth structure, and the change, the deformation is happening differently in response to a given load. And then some of this pattern is due to the load itself being different because the sea level feedback has changed the evolution of the ice in response to the changing climate. I hope that was the question you asked.
Let me follow up with another question that seems to be related. which asks, does the recognition that the solid Earth influences ice sheet stability through 3D structure point to episodes during the Cenozoic where solid Earth changes, such as plumes, changing mantle viscosity, have driven ice sheet volume changes? So are we seeing forcing from the mantle, I think?
Yeah, it's interesting. So I think this does have implications. There's both, so there are two ways that Earth structure can influence an ice sheet. There's both the deformation of the Earth, but also that areas of low viscosity, higher temperatures sort of warm the base of the ice sheet differently. And so actually an example of this occurring is that over long timescales in Greenland, this is work by Richard Alley and others, have looked at the influence of a hotspot traveling underneath the Greenland ice sheet and that changing the heat that's delivered to the base of the ice sheet during different geological time periods. So, so there is sort of in the deeper time, these effects may also be important.
And I guess another point I might add is some work that Jackie Alsterman, formerly of our group, has done, where she has shown that dynamic topography, that is the up and down vertical motions of plates driven by mantle convective flow, change bedrock elevation. And what Jackie showed in a paper now a few years old was that the Wilkes subglacial basin in the East Antarctic has been in a situation of uplift over the last 3 million years. And so that its bed during the mid-Pliocene warm period 3 million years ago was actually on the order of 100 meters lower than it is today. And she showed that reconstructions of ice sheet stability in that area need to account for this bedrock subsidence or elevation going forward in time. There's lots of geological evidence, for example, that during the mid-Pliocene, the Wilkes subglacial basin was more dynamic than models had shown it to be. And Jackie showed that if you correct for this 100-meter change in bedrock elevations, the Wilkes subglacial basin, just as Natalya has discussed, you're getting into deeper water, you become more unstable, and you reconcile the geological evidence for a dynamic East Antarctic ice sheet during that time. And so that's another example. Natalya talked about heat flow, which is very important. Another example is how mantle processes influence the topography of the bedrock or the elevation of bedrock and how it would have changed through the entire Cenozoic. And so I think that's an area that's still largely unexplored, but would be interesting to follow up on.
So another question, this one from David Wilson, who thanks you for the very nice talks. Natalya, could you comment on the implications of mantle viscosity variations for the sensitivity of warming of marine-based ice in the West Antarctic ice sheet and East Antarctic ice sheet? Is marine ice in the East Antarctic ice sheet more likely to retreat?
Yeah, so we have a situation where the West Antarctic has rapidly uplifting bed in response to the ice loss. But in many areas of the East Antarctic where we have a thick, cratonic structure and higher viscosity, the uplift is slower. So the effect is still there, but it would be less effective because the uplift is slower. And so the ice sheet retreat would sort of continue before you uplifted the bed enough to stabilize it. So the effect is still there, but it may be lesser than if you consider an area of really rapidly uplifting bed.
Great. I would like to ask a question. With regard to the fingerprint of ice loss for a particular region, is there data that can be used to validate that pattern in detail at present, or is that beyond the sensitivity of the data, the resolution power of the data?
Well, I mean, the study I referred to, Carling Hayes study that was published in Nature a few years ago, argued that on the basis of tide gauge records, while it was possible to improve estimates of global mean sea level, those tide gauge records, because they're sparse, they have data gaps, they're noisy, on the basis of those alone, it wasn't possible to extract the relative contributions from individual polar ice sheets and glaciers. However, I think a combined, and this is where the field is going, combining information from GRACE gravity studies, for example, with tide gauges, adding in satellite altimetry records, for example, I think there's ample evidence that even the existing record, one can pull out from it evidence of these individual fingerprints. The important thing, Rich, is that you get, the most important thing is that you get data from as close to the ice sheet as possible, because that's where the fingerprints are so amplified. And so Natalya is doing work on that. Natalya, you might mention the work that you're doing with GPS receivers there as a way to detect fingerprints more quickly than a traditional tide gauge record might provide them.
Yeah, so it's tricky to put instruments right near melting ice sheets. It's a really sort of harsh climate, and it's hard to get back there frequently to maintain things. But one of the, we know how to do GPS in polar regions really well. And so one of the ideas is you can actually use the reflected signals from that a GPS antenna receives that reflect off of the water surface first, and then come to the antenna to detect water level changes. So you can use a GPS sort of like a tide gauge. And so one of the things we're doing, if you could do this, you could put a network of GPS near a melting ice sheet to capture that sort of strong gradient in sea level change leading up to the ice sheet. So that's sort of a promising way to get more instruments near the ice sheet and use the existing instruments we have as well.
Rich, would it be possible for Natalya and I to, there's a question here that really strikes to the heart of what Natalya and I have been doing recently, and it asks whether we've worked with indigenous communities.
That's exactly what I was going to next, so please.
And in fact, we have done that. Natalya herself has gone up and trained indigenous communities on the sort of physics of sea level change. We are funded and have connected directly with indigenous communities in James Bay. Natalya's reference here of two papers by Leonard Tuji, who's an environmental health and anthropologist who deals almost exclusively with indigenous communities. And I'll give you an idea of how that connection has worked. One of the applications we've looked at is that helps these communities are the Cree and Inuit in subarctic Canada have hunting routes that are changing now. Those hunting routes were the same year after year and involved sea ice. But of course, now sea ice is more difficult to predict one year to another in our progressively warming world. And so we are currently working to provide those communities with sort of GPS-like devices so that hunters who proceed along a particularly successful hunting route can record that, and other hunters that come after them can use those routes, right? Because sea ice packs are changing from year to year. Another interesting issue, and this involves both Natalya and I, is that land claim treaties in Canada are written for a millennium, not 999 years. And these Inuit and Cree communities in their land claim treaties that they've signed have rights to resources on islands in Hudson Bay and James Bay. However, of course, sea level is falling in those regions. That's being counteracted by modern sea level. And these two papers from 2009 and 2016 project sea level changes in the future, because depending on that interaction between the ice age signal in which sea level is falling and a modern signal in which sea level is probably rising in Hudson Bay, depending on that interaction, some of those islands may connect to the mainland in the next 100 or 200 years. And the problem for indigenous communities in that case is that they will lose the rights to the resources on those islands once they connect to the mainland. So that's led to an opening of a number of land claim treaties so that the Inuit and Cree can rewrite them, renegotiate them to make clear that the rights that they have today will exist in perpetuity, given these sorts of geophysical processes. So I think I can talk for Natlya and I in saying that's been a really rewarding part of our research in looking at those aspects of our field that have direct effects on those communities.
We still have about 5 minutes if you're willing to carry on answering questions.
Yeah.
I'd like to cherry pick one from the Q&A. Where has it gone? Is there something special about having ice sheets that are located far away from each other on the globe in terms of the ice sheet fingerprints and the feedbacks? Would the ice overall be more stable if there were only the Antarctic ice sheet, for example?
Yeah, I can jump in with that. So what the location of ice sheets relative to each other really strongly changes the signal that one ice sheet sees. So we've seen that the Northern Hemisphere ice sheets retreating leads to, they were really a large change in the Northern Hemisphere ice sheet during the last deglaciation, for example, compared to the change in the Antarctic ice sheet. And so this drives a significant sea level rise during the deglaciation that really does increase the ice loss from the Antarctic ice sheet. So in this sense, yes, if we didn't have far away ice sheets melting, what the Antarctic did would look quite different. This is a paper that this is in recent work it's going to be coming out soon. And so if the ice sheet was much closer, of course, an ice sheet melting itself produces a sea level fall that's an order of magnitude larger than the sea level rise farther away. So you really need lots of ice happening in one location or really fast in one location to drive a change in another in order to sort of overcome the local sea level fall associated with that glacier itself.
I'd like to just add on to that and ask whether the current configuration of ice sheets or the current, especially Antarctica, would have been different if the 3D structure of the viscosity beneath Antarctica were different. That is, if you ran a forward model starting from the last glacial minimum, of building up to the last glacial maximum, so from the previous glacial minimum, would you have found a very different configuration of ice if the rheology were different?
Yeah, so the this sort of marine terminating feedback is active, not only dependent on the depth of the bedrock, but also if you raise the bedrock, you're pushing the ice sheet up higher into the atmosphere. This is particularly relevant for Northern Hemisphere ice sheets, but also the Antarctic. So you would have a different sort of boundary conditions at the bottom where you have shallower waters overall, and also higher ice into the atmosphere. So both of those effects would produce a different configuration. If you sort of spin up an ice sheet, build an ice sheet on a higher or lower bed, you do see a different configuration.
I would add in that, and Natalya's not talking about other important work she's done, which looked at projections of Antarctic evolution and how those projections are influenced by that same 3D structure. A beautiful paper, 2018 or 19, that Natlya wrote. So even moving forward, that 3D structure is going to have importance.
I guess does that place constraints on the 3D structure itself? I should ask talks from the Q&A. Tim Craig, who can't post to the Q&A, asks, says, great talk. A lot of the variability in uplift rates in Antarctica seems to be quite short wavelength, hundreds rather than thousands of kilometers. How accurate are the viscosity constraints at relatively shallow depth / short wavelength? And is this a problem, or does it limit your resolution?
Yeah, so I think this gets at one of the uncertainties in this work is that going from seismic tomography to a viscosity structure involves quite a bit of uncertainty. We can use things like relative sea level records and paleo records to try to understand a little bit better one way or the other, but it's sort of, it is a source of uncertainty as opposed to a definitive viscosity that we have. So I think, well, there are multiple lines of evidence, geological evidence, seismic evidence that suggests that that the West Antarctic is sort of this ancient rift zone that's lower viscosity, and the East Antarctic is a craton. The specific viscosity at a particular location is still sort of an active area, and the resolution needed to make these types of predictions is still really an active area of research.
Let me,
there's the sort of PoleNet project. I think, Natalya, you're peripherally involved in that. These are efforts, they're ongoing efforts to try to constrain viscosity variations now that maybe the resolution may be 50 kilometers, 100 kilometers or so, to bring that down. Those local variations are going to be important in the dynamics.
And we have come quite a long way in a short time in resolving from seismic, seismology work to resolving the structure at higher resolutions. Doug Ween's group is a group who works on that, for example.
I'd like to get in one more question before we go, from Jerome Neufeld, who says, Natalya, Jerry, great talk. Out of curiosity, does the induced mantle flow alter the geothermal heat flux at the base of the ice sheet? That is, might it change not only the topography on which the ice sheet flows, but also the basal conditions?
Yes, so that's another area that is, there's some uncertainty around the magnitude of that effect, but changing the structure, the heat of the material, the earth material below does change the heat delivered to the base of the ice sheet, which in turn, the basal hydrology beneath the ice sheet in these areas, or ice sheets in general, is really important for the dynamics. If you have a really wet bed, the ice slides more easily along it, which impacts how much ice is lost and how thick the ice can grow during colder periods, for example. So that is also an important effect that's being looked at.
I might add that, just because it may be the last question, that a little known fact is that Jerome Neufeld spent a year in our group at master's thing, and I often tell Jerome that despite the fact he only spent 9 months with us, I still take full credit for his career success. So.
All right, I think on that note, we should thank our speakers again, and thank everyone who's attending via Zoom and YouTube. So thank you, Natalya and Jerry. And also remind everyone to please check our webpage and Twitter feed to keep track of upcoming seminars. Our next event is 2 weeks from today, when Dr. Laura Wallace and Dr. Emily Warren Smith will give a talk entitled Putting a Finger on the Pulse of Slow Motion Earthquakes. So we hope to see everyone then, and thanks again. Bye-bye.